ladies and gentlemen, it's my great honor to be invited here to give a short talk about recent research. And I'm very happy because, you know, it's quite difficult for me to come to China, my motherland, and because there is some trouble here, we don't have enough, you know, pandemic treatment. So I have to wait for the vaccines. And many of my friends ask me when you will come back to China. I hope I can go back in a few months. So here, I would like to introduce the recent research topics, the influence of acid environment and the temperature on mechanical behavior of cement-treated Masado, and its numerical modeling with Thermo-Elastoviscoplastic Model. I remember that just last year, I gave a similar topics of this research in the summer seminars held by Professor Jiang Jing of Tianjin University. So I don't want to repeat the same things, just give a brief introduction about this research, the background, and give some detailed introduction to numerical modeling, because this is what I want to emphasize here. The background is that maybe some people know that in the past 20 years, we have one of the greatest projects in Japan, which called New Tokyo-Osaka Expressway project, connecting the Tokyo metropolitans and Osaka metropolitans. So in the areas, in the central areas where I live, we constructed 55 kilometers of expressways. The problem is that during the construction, we faced with a very serious problems of settlement of elevated bridges along 5 kilometers, which was never been seen in the history of Japan highway construction. The problems, after we surveyed completely, very detailed and find, I hope you can see the mouse, and you can see this is a direct foundations located on the soft ground, which composed of decomposed granite. The yellow one is a fresh one, and this a little bit deep yellow one is a decomposed granite, and the pink is a completely decomposed granite. And here in Japan, we call it Masado. The problem is that the Masado look like materials, but very strong, are very weak. You even compress your thumbs to deform the soil. It's really a soil, not rock. It's okay? Can you hear me?
Yes, we can hear you.
Okay. So the supporting layer is supposed to be the completely decomposed granite. However, based on design code, it's okay for the bearing capacity, but the stiffness of the soil is not sufficient enough. So the settlement caused by the construction of foundation and reclaimed ground give rise to intolerable settlements from 5 centimeters to several 10 centimeters. So all the construction was stopped for 1 year to make complete the surveys and try to find out some treatment. And then, because I was one of the main technical committee members of this construction project, and 2 technical treatment was proposed. One is the so-called micro pies, not only for pie foundation, but also for direct foundations. And on the other hand, I proposed cement-treated soil, which don't use any pie, but use the cement treat method to enhance the weak layers beneath the foundations. So this is quite cheaper, only one third or 1/4 of what should be spent for micropipe foundation. And then 2 proposal was accepted. The problem is, however, the construction was conducted very successfully, and it has already been open to use. The problem is that in these areas, because in this area we have very active volcanic activities. So for such kind of alkali treatment soils, it is very sensitive to acid environment and also sensitive to the temperature change. In Japan, we have some application case of cement treated soils in the reinforcement of soft ground for temporary structure, but not for permanent structure. However, this time we have to choose this one for permanent structure. So long-term stability of such kind of treatment should be discussed in detail. This is the background of the research and was supported by the Japan Highway Disaster Prevention, the fundings in the 3 years. So in this case, I would like to show you some research process and the research result, and I hope you can take some time to listen to me. The research compares 3 parts. One is the element tests on CTM, cement treated soils, with triaxial compressions creep tests for different acid and temperature conditions. And meanwhile, the microstructure of the soil was also investigated by X-ray fluorescence analysis to find out the change of the alkali ions component. The second is to propose a Thermo-Elastoviscoplastic Model considering the acid effects and try to describe the mechanical behavior of the treatment soils accurately. The third one is that to verify the proposed modified model, both in the element simulations and the FEM analysis. Maybe the audience will be astonished why you should use the finite element analysis to verify the model, because in this case, the element test we conducted is actually not a strict element test. So this is the grain size distribution curve of the Masado. We call the complete decomposed granite as Masado. It is a standard Japanese language. And we also use the cement treated Masados with 5% of cement, because later I will show you the content of the cement will greatly change the mechanical behavior of treated soils. And we find 5% is most suitable to practical real construction site. And also we're using some curing, air curings and water curings with different acid and temperature conditions. And soaking curing, we also carry out soaking curings with different environment as pH values 4, 5, 7 in the constant temperatures 20, 50 degrees, and for 1 week and for 3 weeks. And before we conduct some accurate triaxial compression and creep tests, we at first conduct some uniaxial compression tests to mask which percentage of the cement is the best suited for the field observations. And you can see we conducted a lot of uniaxial compression tests to find a very, nice result, though with some discrepancies, but for uniaxial compression test, the result strength is quite scattering, but you can see we at least conduct 3 to verify the uniformity of the specimens with different temperatures and different curing times. And this is the PC-controlled thermal triaxial test device at NIT, and this is totally computed. Compute controlled, we can conduct it with different stress paths. And also, we have to consider a sealing technique that the samples, the cemetery sample, is very sensitive to water conditions. So during triaxial tests, we have to seal the samples from the waters. So we use the unsaturated techniques, for unsaturated soils to using double cell systems that you can see the cell pressures and the back pressures is totally the same. And during the deformations, the water can flow through the porous metal planes to accurately evaluate the volumetric strain, which is very important for us to modeling the mechanical behavior of the soils. And you can see this is a compression test. Many tests, at least for each case, at least 2 times to verify if the data is convincing. And here I just show you some result of triaxial compression test. We only presented one of them, and I'm sure that all the tests can be repeated very well in the test. It's very interesting that you can see that one of the main purpose for us is to understand the acid conditions and the temperature conditions play what kind of influence on the mechanical behaviors. And you can see for the pH value with 4, the red is quite low and with lower dilatancy. But for pH 7, the complete neutral conditions with very high shear stress strength. So it's quite good for different confining pressures, different temperature, and all show the same tendency. So first, we get the mechanical behaviors on the hypothesis that the test is on the element conditions. And this is just, because we want to model the behavior. So we have to understand the critical stress ratio, shear stress ratio at the critical state. The constitutive model is based on the critical state concept. However, the problem here is that even the shear actual strain reached to 10%, you can still see shear dilatancy is not stable, it still increase, which means that we cannot.
Power on, pairing, connected.
It's okay? It's okay?
Yes, yes.
Somebody is asking question. So
no, some noise.
The problem is that in this case, we couldn't get the accurate value of the shear stress at the critical state because it doesn't reach the critical state yet. So In the modeling, we have to make some treatments. Later, I will give a detailed description. Here, as we say, that critical state has not yet been reached. So we guess this year's value is around 90% to 95%. And also for the creep failure test, you can find, in some cases, it does creep fail in the, for instance, in the pH value equal to 7. You would be a little bit puzzled by this result, but don't worry about that because the creep failure stress is assigned as 95% of what the strength obtained in the compression test. So in this way, 95% of the shear strength for pH 7 is much larger than those of pH 4 and pH 5. And we don't find the material has creep behaviors. Okay. So on the other hand, we also conduct X-ray fluorescence analysis. And because it's different, you can see this is the radius of the sample with 5 centimeters. 5 centimeters. Okay. So the out and the inner place, the erosion of the calcium ions by acid environment is totally different. So we have to measure the content of this erosion very carefully. And as you know, we sliced to 6 layers and then pick up the many samples at the same place. You can see this is just for one net plate for one samples, hundreds of them. And you can see here, you can find the ratio of calcium's ion, relative ratio. The solution, is quite different. So in this case, you can see this is the distance from the center of the samples. In the centers, the relative ratio, which defined as the calcium percentage before soaking and after soaking, you can see in the center, because it's far from the surface, there is no any erosion. However, in the surface, the erosion is quite serious. Or you can see decrease to almost 30%, 70% lost. So you can see the sample is no longer, accuracy is no longer an element. It is a boundary value problem. And then we can see some, calcium ions distributions with regression analysis. And you can see they are all linear distributed with the distance. So it's quite easy for us to do some regression analysis. And then you can see the proposal of constitutive model comes here, a serious question, because this is a so-called superloading and subloading constitutive model, the concept firstly proposed by Professor Hashingchi and Professor Asaoka, and also the transformed stress tensors called TIJ stress to consider the intermediate stress difference. So this is the stress latency relation with TIJ stress space. So it's a quite matured constitutive model. However, in this case, the shear stress ratio at critical state is no longer a constant value. It depends on the acid constitutions, the temperatures, and also the confining stress. So that's why we have to remove this constitutive model again. So you can see some modification of the constitutive model. First of all, we have to propose the capital mu should be formulated as a function of the relative, solution and the stress, the temperature, okay. And you can see this is one result between the capital mu C and the temperature under different confining stress. For different confining stress, the blue and the red are different. So we still have to move ahead. So you can find the regression via relation, strong relation can be obtained. And finally, we get a very nice regression analysis result with a linear, almost linear relations between the capital mu, the relative ratio of Ca, the temperatures, and the initial confining stress. So by these definitions, we can find, though the material parameters change from 1 to 4, alpha, beta, gamma, and theta, but all these ones are uniquely defined irrespective what kind of, the solutions, the temperatures, and the initial confining stress. So you can see, this is the constitutive model. They use 10, before they used 10 parameters, which the first 5 are totally the same as those in chemical models. And there are 5 parameters to describe the shape of the yielding functions, the decaying of the consolidations, and over structures. However, for the capital mu, we have to divide it to 4. All these 4 parameters can be determined easily with definite materials. So in this case, all these parameters are independent of the state parameters, different conditions. And then you can see this is the performance of the constitutive model. So here we find that the capital mu C should be estimated by 90% of the values at the shear stress ratio at the axial strength equal to 10%, but still not reached to a critical state. So by this treatment, we can see the simulation is quite good, can describe very nicely, quantitatively, with the behavior of the soils. And also some creep behaviors. Here I should emphasize that all parameters used, all these tests are just use one set of the constitutive model. So we can say it's a really material parameters, not a fitting parameter. Then the problem is that I have to emphasize here is that because you see the erosion of the soil, the calcium ion is dependent on the distance from the surface of the solutions. So this is actually is a not uniform distributed, element behaviors. It's a boundary value problem. Then the question is that the constitutive model proposed here is still valid for such kind of non-element behaviors. In other words, the inference of these non-element behaviors reach to what kind of content should be neglected or cannot be neglected. So then we conduct the finite element analysis, taking this so-called element test as a boundary value problems, and just put into all the constitutive material parameters to one set, and take this one as a boundary value problem, and solve it, and to find out If,
Okay, Professor Zhang, you have 2 minutes.
yes, this is the last slide. Don't worry
Okay.
about it. Yeah. And you can see it does affect sometimes. In some cases, you can see the dashed red line represents the 3D simulations. Okay, this is the vertical stress and vertical strain relations. It's obtained by average of all the elements. You can see it looks like similar, but sometimes have 0% to 10% of the errors, and sometimes it is different. You can see that one element simulation represents the constitutive models predictions, right? So in this case, you can find the softening behavior is not in the same order, which is totally contribute to the string localizations in the calculations. So the question, the concluding mark, from the triaxial compression and creep test and XRF analysis, it is confirmed that the change in acid environment and temperature may affect significantly the mechanical behavior of cement treated materials. And the constitutive model proposed here can well describe behavior of element, so-called element, but this actually is not an element test. Based on the model, we can see that there is some errors, but still tolerable. So in this case, we can say the element test is still useful for the modeling of the element, for the modeling of the soil. Thank you for your attention.
Okay. Thank you very much, Professor Zhang, for your excellent presentation. It's a very interesting topic.